For the student of electricity, a knowledge of the basic concepts of voltage and current is essential. To establish a firm background, we should master the fundamentals of alternating and direct current generation. To begin our study, let's first review a basic principle to see how current is generated. In 1831, Michael Faraday announced the principle of electromagnetic induction. A magnetic field will induce a voltage in a conductor if the conductor cuts through the magnetic lines of force. Voltage and current generated in this manner are called induced voltages and induced currents. In terms of producing electric power, this means that a generator can convert mechanical energy, such as that derived from steam or water, into electrical energy. Before we examine the electrical generator, we should know the direction of the induced voltage and current in the electric circuit. In modern electron theory, the flow of electrons is from the negative to the positive terminal. However, Benjamin Franklin defined electric current flow to be from the positive to the negative terminal, and we have used this conventional current flow ever since. To determine current direction, we use Fleming's right-hand rule for generators. Extend the thumb, forefinger, and center finger of your right hand so they are at right angles to one another. Point the forefinger in the direction of the magnetic field, from the north to the south pole, and the thumb in the direction of the conductor's motion. Your center finger then points in the direction of the induced current. You might remember that F is for forefinger and field, T is for thumb and thrust, and C is for center finger and current. To generate a usable voltage that produces current when the circuit is completed, the part of the conductor in the magnetic field should be made very long. This is accomplished by constructing coils. With a coil of several turns, other conditions being the same, we find the voltmeter deflection is greater than that for a coil with a single turn, indicating a greater voltage. This is because the total induced voltage is the sum of the induced voltages in the individual turns. Therefore, we can say the total induced voltage is directly proportional to the total length of the conductor in the magnetic field. To make this principle more evident, let's connect the voltmeter to a coil with hundreds of turns. This time we'll pass the magnet through the coil, for it makes no difference if the field or the coil is moving. You will notice there's an even greater deflection of the voltmeter because the total voltage is the sum of the voltages induced in each of the hundreds of coil turns. Another factor which determines the total induced voltage is the velocity of the coil in the magnetic field. The faster the rotation, the faster the coil cuts through the lines of force, and the greater the induced voltage. Thus, the induced voltage is directly proportional to the velocity at which the conductor cuts through the lines of magnetic force. The third factor determining the total induced voltage is the strength of the magnetic field. To demonstrate this, we will substitute an electromagnet for the permanent magnet, allowing us to control the strength of the field. If we now increase the DC current that excites the magnet, the field of the magnet becomes stronger, and we find the stronger the field, the greater the induced voltage. Induced voltage then depends on three factors: the total length of the conductor in the magnetic field, the velocity of the conductor, and the strength of the field. To calculate the total induced voltage, use the formula E equals beta LV over 10 to the 8th. Beta is the flux density of the magnetic field. L is the total length of the conductor in the magnetic field. V is the velocity of the conductor. And 10 to the 8th represents the 100 million lines of force which must be cut per second to induce 1 volt. It should be obvious that we must continue to rotate the coil in the magnetic field if we want the electric current and voltage to continue. Let's examine this rotation more closely to see how a generator works and to understand the nature of alternating current. The particles flowing in the circuit represent electrons, but keep in mind the conventional current flow is opposite in direction. In a simple generator that's connected to an electric light, the greatest current is produced when the conductor passes through the magnetic lines of force at the fastest rate. This occurs when the conductor moves at right angles to the field. As the conductor continues in its rotation at a constant speed, it cuts through the magnetic field slower and slower because it moves at smaller and smaller angles to the field. Therefore, less current is induced. When the conductor moves parallel to the field, no current flows because the conductor doesn't cut through any lines of force. This occurs twice in each revolution. As the coil rotates, one of its sides cuts downward through the magnetic field, causing current to be induced in one direction, and while one side moves downward, the other side is moving upward, inducing current in the opposite direction. After the coil passes through the position of no current flow, the previous downward side moves up, and the previous upward side moves down, thus reversing the current flow in the external circuit. This, then, is alternating current, a flow of current in a circuit which reverses direction periodically and is continually varying in strength. The current flow is caused by an induced alternating voltage. If we plot this movement on a graph, we will find that the voltage rises from 0 to a maximum value in one direction. We'll call this maximum positive voltage. Then the voltage decreases to 0 and rises to the same value in the opposite direction, maximum negative voltage. Then it again decreases to 0. In alternating current, this voltage pattern is repeated at equal intervals of time. The pattern, which represents the direction of the voltage, is called a sine wave. If we plot the pattern of the current's direction, we find that it too is a sine wave. However, since the voltage and current sine waves are in phase in simple resistive circuits, such as with an electric light, that is, they pass through their 0 points at the same time, we will plot only the voltage wave to illustrate the flow of alternating current. Now let's see how the sine wave relates to the movement of the coil in the magnetic field by looking at a cross-section of one conductor. The conductor's rotation of 360 mechanical degrees produces a voltage sine wave of 360 electrical degrees. The magnitude of the voltage which is generated is a function of the number of lines of force the coil passes through. As it passes the 90-degree and 270-degree positions, the coil cuts through the most lines of force per unit of time. At these points, the maximum values of the voltage sine wave are produced. As the coil passes through the 0 and 180-degree positions, it moves parallel to the lines of force, and no voltage is induced. These positions are the 0 points of the sine wave. If we connect a simple AC generator to an oscilloscope, we can observe the formation of the sine wave. Each time the coil approaches the north and south pole, the sine wave reaches its maximum values. A sine wave of 360 degrees is called a cycle, and we call the number of cycles per second the frequency of the voltage or current. The voltage and current in your home, for example, has a frequency of 60 cycles per second. This means the current in the circuit rises from 0 to its maximum positive voltage, back to 0, then to its maximum negative voltage, and back to 0, 60 times each second. The oscilloscope can help us see different frequencies. It represents a 60-cycle wave on the screen by one cycle of the sine wave. If we double the alternating current's frequency to 120 cycles per second, 2 cycles are displayed in the same time interval. As we continue to alter the frequency, the oscilloscope allows us to observe this change. In a generator, the space through which the coil or rotor must be moved to produce 1 cycle depends on the number of magnetic poles in the generator. In a 2-pole generator, for example, it must make 1 complete revolution. Therefore, 360 mechanical degrees is equivalent to 360 electrical degrees, or 1 cycle. In a 4-pole generator, however, the coil need only move through 180 mechanical degrees for 1 complete cycle, or 360 electrical degrees. Each complete mechanical revolution then produces 2 cycles. Some generators, such as those run by water power, have many poles, so they may operate at slow speeds to generate 60 cycles. Thus far, we have been discussing single-phase current which is generated by 1 rotating coil. In practice, however, 3-phase voltage is generated in electric power systems. In a 3-phase generator, 3 coils are placed 120 electrical degrees apart. Then, the 3 voltages which are generated are 120 electrical degrees apart. This means that 3 different currents are generated, each one displaced from the others by 120 electrical degrees. 3-phase generators are popular because they make more efficient use of the generator's iron core and its copper windings than do single-phase generators. 3-phase current can be distributed more efficiently than single-phase current. And large 3-phase motors run better and are less expensive than single-phase motors. In addition, a major reason alternating current is used over direct current in electric power systems is that it can be transformed easily to different voltage levels. However, AC cannot be used in certain applications. Some electrical equipment requires current flow in a constant direction, direct current. The AC generator itself must be supplied with direct current for its magnetic field. However, we have seen that a magnetic field will induce an alternating voltage and current in a rotating coil. Therefore, to change an AC generator to one that generates direct current, we must find a way to maintain a current flow in 1 direction in the external circuit. To do this, we need only change the slip rings which collect alternating current to a commutator, which will rectify, that is, change AC to DC. The commutator is simply a ring that is divided into segments, each insulated one from the other. One end of the coil is attached to 1 ring segment, the other end is attached to another segment. Now, as the coil rotates through the first half cycle, the induced current of 1 direction is collected from the commutator segment. It flows through the external circuit, then back to another commutator segment and the coil, completing the circuit. If the contact would continue, as it did in the AC generator, the current in the circuit would reverse its direction. But the brush, which connects the commutator to the external circuit, breaks contact with the first commutator segment and makes contact with the second. The induced current in the rotating coil is now opposite in direction from that of the previous half cycle. But since the commutator has switched the coil connections to the opposite sides of the circuit, the induced current from the second half cycle again passes through the external circuit in the same direction. As far as the external circuit knows, the current generated from the second half cycle is in the same direction as that generated from the first half cycle. The commutator has rectified the current, converting it from an alternating negative-positive current to one that flows only in 1 direction, direct current. However, direct current produced by a single coil would be pulsating and unsuitable for most applications. Therefore, practical generators have many coils and many commutator segments. The resultant DC voltage from these generators is usable because it pulsates very slightly. Let's now compare the AC generator with the DC generator. The AC generator is used for the generation of most of our power because it can be built with larger power and voltage ratings. A steam turbine generator might be rated at 500 million watts and 13,800 volts. This high power and voltage is possible because the generator's output connections are attached to the stator, or stationary part of the generator. The rotor, which provides the magnetic field, is supplied with direct current of possibly 500 volts. This is supplied by a DC generator called an exciter, which is often located at the end of the AC generator. The turbine uses the mechanical energy of steam to drive the generator. As the electric power demand increases, the turbine's governor allows more steam into the turbine to keep the generator running at a constant speed, or frequency. At the same time, the exciter will cause the generator's DC field current to increase in order to maintain a constant magnitude of the generated AC voltage. Now let's look at the DC generator. In the direct current generator, the field poles, which establish the magnetic field, are stationary. The armature, which contains the commutator, must be the rotating part, so that the stationary brushes can collect the current, rectifying it by switching the load current from one set of commutator segments to another. However, the DC generator is limited in capacity because high voltages would cause damaging arcing at the commutator. Therefore, because they are seldom rated as high as 750 volts, they are used only for the generation of power in specialized applications. Today, we are using staggering amounts of electric power. And as you continue to learn more about modern technology, you will find the basic concepts of current generation are of major importance. In review, let's look at a special generator which has an armature with both slip rings and a commutator. When connected to the slip rings, the voltmeter indicates alternating current is being generated as the armature is rotated. When connected to the commutator, a flow of direct current is indicated. So we can see that in the generation of both AC and DC, voltage is induced by a conductor cutting through lines of magnetic force. The total induced voltage is directly proportional to the total length of the conductor in the field, the velocity of the conductor, and the strength of the magnetic field. Alternating current reverses direction periodically. Its flow is represented by a sine wave. On the other hand, direct current is a continuous flow of current in one direction. The fundamentals of alternating current and direct current generation are essential for your understanding of electricity. Learn these concepts thoroughly, and you will have a firm basis for the continuing study of AC and DC circuits. Learn these concepts thoroughly, and you will have a firm basis for the continuing study of AC and DC circuits.